Welcome to a little bit of everything. I'm Adam, and then the topic for today is on the derivation of the shape of satellite orbits. So, let me just give you a brief introduction to this topic. So, why is this topic important? Actually, what is really important is not about the satellite orbit itself, but rather the method of derivation for the satellite orbit. Once you have mastered this method of derivation, you can use this as a tool to derive other type of orbits, such as, let's say we have a spring system, such as an orbit system, we have a mass on the spring and it is orbiting around like this. Then for any type of central field systems, we can use the same method of derivation to find the shape of this orbit. Now, let us just get on to the derivation itself. So first of all, there's a few things which you have to know beforehand. The first one is Newton's second law. So the sum of all the forces acting on a particle is equals to its mass multiplied by its acceleration. And the second thing you should have already known is the conservation of energy. The kinetic energy added by the potential energy is conserved, E, where E is a constant, if and only if the force field is conservative. The third one is the conservation of angular momentum about the axis O if the force field is a central force field, so there's no resultant torque acting on the particle about the axis O. So these are the three things which you have to know in order to derive the equation of motion and therefore the shape of the orbit for the satellite. So let's just get on to it. Okay. So there's two methods to derive the equation of motion for the satellite. The first method is by Newton's second law. So let's just talk through that for now. So the first method is by Newton's second law. Okay, so we have a planet in the middle. We have an orbit of a moon about that planet. And so we're using polar coordinates in this case. So this is R. We'll take this as O, the center of the orbit. Sorry, the reference point. And this is the position vector R. E theta will be in this direction. In ER is in this direction. And K will be going out of the page. Okay. So a few things to note. We have a gravitational force acting on the particle. So there's a few assumptions. We assume that the mass of this is very, very large. So this mass is very, very large compared to this mass. So so we can consider this mass to be stationary and at point O. So these are point masses, by the way. Okay, so let's just take a look at the forces acting on it. So it's quite obvious. There's only one force acting on the particle, which is gravitational force. Let me just use a different color. And this is GMM over R squared acting in a negative ER direction. Okay. Now let's just resolve forces. But before that, we have to look at the acceleration equation. We know that the acceleration of this particle, let's just call it p. So this is like p. The acceleration of p can be written as r dot dot minus r theta dot squared, the centripetal force, the ER direction, plus 2r dot theta dot, the Coriolis acceleration, which we have in this case, but we're not going to look into that for now. So the Coriolis acceleration and r theta dot dot. E theta direction. Okay, so what we're concerning with ourselves with is in the ER direction. So let's just resolve forces in the ER direction. So in the ER direction, we have negative G mm over r squared and this is equal to the mass multiplied by r dot dot minus r theta dot squared. Okay, let me just clear the... Okay, so now let's take a look at this equation. We have two variables right now. We have r as a variable, we have theta dot as a variable, and that's going to be quite a problem, so we have to eliminate one of them. Now let's think about it for a while. Remember that the force field is a central force field, and therefore angular momentum must be conserved. And coincidentally, in the angular momentum equation, we have theta dot and we have r as well, so we can eliminate one of the variables. So we know that, we know that the angular momentum h about axis O is equals to r theta dot squared. Remember v equals r theta dot, and therefore n r theta dot squared, and therefore mr squared theta dot, and therefore theta dot will be equals to h naught over mr squared. Okay, so let's just substitute this into this equation, and also remember that h naught is constant, so we only have one variable r here. So negative gmm over r squared, we can just eliminate m along the way. It's equal to r dot dot minus r multiplied by h o squared divided by m squared r4, and therefore let me just clean off this thing. R dot dot, the final expression we have, which is the equation of motion, is h naught is r dot dot over h o squared over m squared r cubed plus gm over r squared. And this is equal to 0. Now this is the equation of motion for the satellite orbit. To simplify things further, just to make things more convenient, we will remove this term and replace it by a single constant, since h O and M are both constants. And we call this the specific angular momentum. So we let HO equals to HO over M. This is called the specific angular momentum. And we substitute it back in, and we'll get the final general expression, which is r dot dot minus HO squared head squared over r cubed plus GM over r squared equals to 0. Now I'm going to end the video here, and I'm going to continue on in the next video and talk about the other derivation using conservation of energy.